These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. Upstream, the velocity gradient is fairly large. Downstream, it is much less. This composite photograph compares the two velocity profiles. Because there is no vorticity upstream of the plate, and because the circulation per unit length along it is constant, we conclude that all of the vorticity in the boundary layer is introduced at the leading edge. But the distribution of vorticity normal to the plate changes along its length. Upstream, 95% of the total vorticity is contained within this area. Downstream, 95% of the total vorticity is contained within this area. Viscosity acts through the mechanism of molecular diffusion to spread out the vorticity as it is convected downstream. The local boundary layer thickness is a measure of the distance vorticity has diffused away from the plate. We can relate the factors controlling this growth process in the following simplified manner. The diffusion length delta increases as the square root of the product of the kinematic viscosity nu and the time of diffusion t. Here's the normal flow. We will speed up the flow. Now, the flow velocity outside the boundary layer has increased. At any position along the plate, the boundary layer thickness is now less than before, because with a higher mainstream velocity, the boundary layer has had less time to grow. slow contraction, and watch the boundary layer along the flat side. The upstream boundary layer is growing slowly as it enters the contraction. After the contraction, the boundary layer is thinner. Note that the distance from the wall to the streamline downstream is about half what it is upstream, because the two-dimensional flow contracts 2 to 1. In the contraction, the effect of the pressure gradient in the boundary layer is to enhance the already high shear stress or vorticity concentration very near the wall. It is as though a new boundary layer were being generated within the old. The combined profile at the exit is relatively thinner because there has been little time for growth of the new boundary layer by viscous diffusion. Using vorticity arguments, we can see that the vorticity added to the boundary layer by the contraction has had little time to diffuse. So downstream, a turbulent boundary layer can withstand a larger unfavorable pressure gradient without separating. We shall again examine the flow along a flat plate. The boundary layer on the bottom side is laminar and two-dimensional. On the top side, the boundary layer has been tripped by a wire placed well upstream. Unsteady motions in the turbulent boundary layer are three-dimensional. Some of the motions are perpendicular to the plane of view. These timelines correspond closely to the instantaneous velocity profiles for the two types of boundary layers. Superimposing a number of displacement lines enables us to obtain a mean velocity profile for the turbulent layer and the laminar layer, and at the same time gives an experimental notion as to where the fluctuations occur and how large they are in the plane of mean motion. In this photograph, we can compare mean laminar and turbulent profiles. Here is the laminar one, the turbulent one. And here they are superimposed. The velocity gradient normal to the plate is larger for the turbulent layer, and it therefore has a larger wall shear stress or drag. The circulation is the same. Distribution of vorticity in the two layers is very different. There is more vorticity near the plate in the turbulent layer. The distribution of momentum in the two layers is also different. In the turbulent layer, high momentum fluid is moved toward the plate, and low momentum fluid is moved away from the plate by unsteady, random motions. There are larger shear stresses and more momentum in the turbulent boundary layer than in the laminar layer, and the turbulent boundary layer is slightly thicker.